Today we're going to talk about Newton's three laws of motion. The first and third law tend to be the laws people are more familiar with, and the second law is the one that's a little bit more difficult, but we're going to try to give you guys examples that are going to make it easy for you to use throughout the week. Newton's first law of motion is the law of inertia, and it pretty much says that any object at rest has the tendency to stay at rest, and that any object in motion has the tendency to stay in motion. But here's the important caveat: unless it's acted upon by an unbalanced force, which essentially means, let's take this marker. If I put this marker here on the tray, that marker will stay there forever and always. 10,000 years from now, if another force doesn't act on it, if I don't push it, if there isn't an earthquake to rattle it around, if the wall doesn't fall down and the wind blow it away, 10,000 years from now, it will be there because inertia means that the object has a tendency to stay at rest. Likewise, if an object is in motion, it has a tendency to keep moving along the same path at the same speed forever. Now, we don't see this on the planet Earth because we always have two things that are impacting every object as it moves. One, gravity. Gravity is an unbalanced force that's always pulling objects towards the center of the Earth. And two, it's air resistance, friction with the surface of the air. But in space, in the vacuum of space, if we could remove all the stars, if we could remove all the planets, all the comets, all the aliens, everything, and we threw a baseball and there was nothing to stand in its way, it would travel at the same speed without ever slowing down on the same exact line forever. Newton's second law of motion is the law of momentum. Usually it's easier to give you guys the formula that says force equals mass times acceleration. Now, what this really means is that really big objects take more force to slow down, or really fast moving objects take more force to slow down. Both of them are harder to stop. And that if we applied the same force to two objects of either different speed or different mass, we would have a different result. For example, if I took a golf club and I swung as hard as I could and hit a golf ball, I can drive a golf ball about 250 yards. But if I use the same club with the same amount of force on a basketball, it's not going to fly as far as it would as the golf ball because their masses are different. That's what Newton's second law essentially means. Newton's final law that we're going to work with this year, sorry about that, is the law of reaction. And it says for every action there is an equal and opposite reaction. When you hit a baseball this spring, as the ball presses against the bat, as the bat presses against the ball presses back against the bat with equal and opposite force. When I push down against the concrete pushes back and I jump up. Now, does the concrete actually go? No, of course not. But it provides the same amount of resistance that I push down against the ground and lift off with. Newton's three laws dictate how all objects move, from the smallest atom to entire planets and solar system bodies, okay? Scientists are starting to find out that at the extreme molecular level, things that are hard for human beings to imagine, that these laws might not work out the same way. But for everything that you're going to deal with in science from now through college, unless you become an astrophysicist, pretty much governed by Newton's three laws.